Astronomers were almost certain that these two galaxies would merge in about 5 billion years. It was considered inevitable. But now, new data reveals something shocking. The actual chance of that collision happening might be just 2%. This changes everything we thought we knew about the future of our local universe. Today, you'll discover why scientists may have been wrong, how the true motion of galaxies was finally measured, and what could happen if the cosmic crash we expected never comes. For a long time, the collision between the Milky Way and Andromeda was considered a cosmic certainty. And it wasn't a wild guess. It was based on solid calculations. The best data we had at the time, even though it was incomplete. The logic seemed sound. The Andromeda Galaxy, also known as M31, is moving toward the Milky Way at about 110 kilometers per second. That's over 390,000 kilometers per hour. When something that massive is coming at you that fast, in what looks like a straight line, it's only natural to assume it's going to crash. And for decades, astronomers did just that. Early measurements using spectroscopy detected a blue shift in Andromeda's light, direct evidence that it's approaching us. Unlike most galaxies in the universe, which are drifting away due to cosmic expansion, Andromeda appeared to be swimming upstream, heading straight for us. That motion was so clear that scientists began to model the future collision. Two giant spiral galaxies merging in a colossal gravitational embrace, forming a new supergalaxy. They even gave it a name, Milky or Lactomeda. The models predicted that in about 4 to 5 billion years, the two galaxies would merge completely. The image was powerful. It showed up in NASA animations, planetarium shows, science books, documentaries, and even memes. The fate was sealed. Collision, fusion, the end of the Milky Way as we know it. But there was a hidden flaw in this narrative. Scientists were only observing radial motion, the straight-line approach speed. They couldn't see the sideways motion, called tangential velocity, and that's a massive detail. Imagine watching a car come toward you, but only being able to tell if it's getting closer or farther. You don't know if it's also moving sideways. If it is, it could simply pass by and never hit you. That's exactly what happened here. We knew Andromeda was moving toward us, but for decades we had no idea if it was also veering off. And measuring that sideways motion was impossible, even with the best telescopes. As a result, models predicted a direct collision because they assumed a straight path. That wasn't a mistake in the math. It was a limitation in our tools. Measuring the sideways movement of a galaxy 2.5 million light-years away requires insane precision, like spotting an ant crawling across the top of the Eiffel Tower while you're standing on another continent. But science doesn't stand still. Eventually, this blind spot began to fade, and with it came a whole new story. Even without a direct collision, the encounter between the Milky Way and Andromeda is going to be brutal. Simulations show that the gravitational forces generated during their approach will be strong enough to completely deform their structures. The spiral arms of both galaxies will begin to stretch and twist long before the point of closest passage. Some of that material will be ripped from the galactic disk and flung outward, forming massive streams of lost stars and detached gas clouds. The galaxy, as we know it today, organized, spiral-shaped, with a well-defined core, will be distorted, beyond recognition, and all of that happens without a single impact. During this approach, thousands of stars will be pulled from their original orbits. Some will form long tidal tails made of hundreds of thousands of suns, slowly moving in chaotic motion. Others will be completely ejected from the gravitational hold of their home galaxy and drift off into intergalactic space, becoming solitary stars. And here's the hard fact: the Sun could be one of them. The chances of our solar system being thrown into a more distant region of the galaxy, or even out into the halo, are real. That doesn't mean destruction, but it does mean isolation. The night sky would become unrecognizable, the constellations would vanish, the entire backdrop of our sky would change forever. Meanwhile, the dwarf galaxies orbiting the Milky Way and Andromeda won't stand a chance. The interaction between the two giants will trigger gravitational chaos that will tear, absorb, or completely shred those smaller systems. They'll be dismantled by tidal forces, and their remains will be scattered or consumed. That's how galaxies grow, by devouring smaller ones, and this encounter will push that process into overdrive. Another guaranteed consequence is the collision of gas clouds. Even if the galactic cores don't crash, their vast interstellar clouds will intersect, and when they do, the compression will trigger intense star formation. A new generation of stars will ignite, especially at the distorted edges of both galaxies. That burst of light will mark the beginning of something new, right in the middle of all the chaos. What's even more mind-blowing is that this won't be a single, sudden event. The first close pass will happen about 4 billion years from now. But the full process, with repeated approaches, gravitational shocks and partial mergers, could take nearly 2 billion years to unfold. It's a slow, escalating spiral of destruction and transformation. Even if there's a 98% chance of no direct collision, the damage is guaranteed. The technical term isn't collision, it's galactic interaction. But the outcome is the same. The original shapes are destroyed, stars are rearranged, and a new structure is born. Now let's talk about the 2%, the narrow chance that the Milky Way and Andromeda won't just pass through each other, but will crash head-on. No near miss, no gentle interaction, a full-scale galactic collision. If this scenario plays out, the gravity wells of both galaxies will lock into a deadly embrace. The central black holes, each with millions of solar masses, will spiral toward one another like titans, drawn by an invisible force, creating shockwaves in space-time that ripple across the universe. In this 2% scenario, nothing stays where it is. The spiral arms, gone, torn apart almost immediately. Hundreds of billions of stars will be violently rerouted, flung from their positions, as gravity rewrites the map in real time. Some systems will be pulled into elongated orbits. Others will crash into dense gas clouds and trigger massive starbursts. Whole regions of the sky will light up with new stars, while others go dark, swallowed by dust and chaos. Think of it as two record players spinning toward each other, and when they touch, the music stops. Only turbulence remains. In this scenario, there's no safe corridor for the solar system to drift through. The chaos is everywhere. Massive clouds of hydrogen and helium will smash into each other, compress, collapse, and ignite. Star formation will skyrocket, especially in the overlapping central zones of the two galaxies. Supernovae will follow, then gamma-ray bursts. Some regions will go sterile, stripped of gas by stellar winds and black hole activity. Others will become star factories, glowing blue with hot, young stars. This is cosmic violence on a scale we can't replicate or even simulate fully. The black holes at the centers of the Milky Way and Andromeda won't just orbit each other. They'll merge. That final moment will release more energy in gravitational waves than all the stars in both galaxies combined emit in light. Space itself will vibrate. The event horizon of the new merged black hole will be larger, more powerful, and more active. It will consume gas clouds, rip apart stars, and flood the core with X-rays and radiation. That central region will become unstable and blindingly bright, a temporary quasar at the heart of our new galaxy. And let's be clear, in a full collision, galactic time slows down. What should take hundreds of millions of years stretches into a billion-year spiral of destruction, merger, and eventual balance. The final structure wouldn't resemble the Milky Way. or Andromeda. It would be something new, a giant elliptical galaxy, round, featureless, and full of stellar ghosts. The remains of two spirals that once danced on the edge of cosmic probability and collided at full speed. The collision of two giant galaxies isn't the end. It's the beginning of a brutal and long transformation. After their cores crash and spiral arms intertwine, what emerges is a new elliptical or irregular galaxy, unstable, chaotic, with structures that defy familiar shapes. At the center, supermassive black holes collide and merge. When that happens, they release gravitational waves so powerful they distort the very fabric of space-time. It's a silent explosion with consequences that can be felt millions of light-years away. The energy released can eject gas and dust from the galaxy, forming relativistic jets that cut through space at near light speed, and it doesn't stop there. For billions of years after the merger, stars will continue to form in bursts. They're born in compressed gas regions, creating stellar nurseries that shine intensely in infrared. These post-merger galaxies can have star formation rates 100 times higher than normal. They become true factories of massive, young, hot stars, often larger than the Sun, but with much shorter lives. Meanwhile, planetary systems that survive the gravitational chaos undergo extreme mutations. Some will be flung out of the galaxy entirely, turning into rogue worlds, wandering alone in the dark between galaxies. Others will be pulled into denser regions, exposed to absurd levels of radiation, and collapse with their stars into supernovae. The new galaxy also loses part of its rotation. The spiral symmetry disappears and gives way to a more diffuse shape, as if chaos has won over order. Over time, it stabilizes, but its internal structure is radically different. No elegant spiral arms, just a monstrously energetic core and a mix of old and newborn stars. And more, these mergers help build the BOO universe as we know it. The giant elliptical galaxies we see today, like M87, likely formed this way, through cosmic collisions and brutal mergers. It's a continuous process that slowly reshapes the visible universe, creating new structures, erasing old ones, and forging the next generation of worlds, stars, and black holes. And this is just the beginning, because the universe still hides bigger collisions, hungrier black holes, and structures we can't even imagine. If you love this kind of deep space journey, hit that subscribe button now. This is Nebulaverse, where space has no limits, and the next frontier is already in the next video.